pirates' boats seafaring.
So we say and so we do.
There's none set sail with finer bearing.
Sailing on the ocean blue.
Greetings and welcome to another exciting lecture in geomorphology. We're back again. We've moved on from fluvial processes and we're moving on to the next portion of the course, and that's talking about our good friend, where are we pointing? Right down there, coastal geomorphology. That's right, we're going to be talking about the different processes that shape coastlines, how quickly those coastlines are modified by geomorphic action, and then towards the end of, not today, but a subsequent lecture, we'll be talking a little bit more about how humans try to control erosion and deposition along coastlines. But that's for a later date. Right now, our goal is to kind of introduce the topics of coastlines, the general morphology of coastlines around the world, what controls that morphology. And then the last part today is really starting to think about the most dominant force that shapes coastlines, and that's waves. So we'll dive in to exploring in a bit more detail about the different types of waves and how waves end up shaping coastlines. So that's our plan for today. The picture behind us is from the beautiful Oregon coast right here. We're looking at Heceta Head in Oregon with a nice lighthouse right here. This is south of Newport in Oregon. Does everyone notice this flat bench right here that the lighthouse is built on? This is a marine terrace. In our next lecture, we'll be talking a little bit more about landforms associated with coastlines, but just a little kind of teaser, right? This flat surface right here, that's a geomorphic surface. When we see flat surfaces in the landscape, that's something that's formed by some sort of geomorphic action. And with these, what we're looking at is essentially wave action that's planed off and formed a flat surface. Now, as you can see in this picture right here, there's a big difference from down here at the coastline all the way up to this platform. So how did coastal processes down here make a flat surface up here? Excellent. I like your thinking. One of two things could have happened. I totally agree with you. Yeah. One, ocean levels could have been higher. And so this could have been the coastline at some former time in the past, or ocean levels haven't gone up. Then the land has come up and we've uplifted the land, we've uplifted and abandoned this marine terrace. This is really, really common along coastlines in the Pacific Northwest because of our active tectonic boundary with lots of subduction as the Juan de Fuca plate's being subducted under the North American plate. So we see tectonism and uplifting of the land surface. So these marine terraces are very common along the Oregon coast, and I encourage you to go check them out because they are spectacular. Okay, are you excited now? I'm excited. Let's jump in and see what's next. Oh, I got to get my clicker going. There we go. First thing I want to mention is that when we look around at different coastlines around the world, we see an incredible variety in the morphologies that coastlines could take. In this top picture here, we see relatively flat coastlines, right? We've got a beach face right here with the swash of the waves coming up and down. We have berms here with a flat kind of surface behind that, where that's where you set up your blanket or your lawn chair and hang out. And then behind that, you might have a nice coastal dune, right? With aeolian sediments with some dune grass on it. And so this is a relatively gentle coastline, but not all coastlines are like that, right? Some coastlines are incredibly rocky and we get sea sacks, these giant, essentially islands of land that stick out off the wave cut platform, and maybe some wave cut terraces in the background. So we can have incredibly rocky coasts with really, really high relief. This picture here is from a movie. And if you can figure out what movie this is from, we'll talk about it in our next class. So it's one of my favorites. Okay, so we can have kind of rocky coasts like that. We can have coasts with bluffs with, look at this, we've got essentially wave action that's been eating into the base of this cliff right here, and it's caused a mass movement. But we've got a flat surface on the top. Then we've got a nice picture here with another kind of rocky coast with a marine terrace. So these are all sorts of morphologies we can see along coasts. And so we need to start to think about what is shaping those morphologies. Why do coasts look different? Why do they not all look the same? Okay, for example, one of the biggest kind of things we can think about is the interaction between rivers and coastlines, and think about how they're different in different places on the globe. For example, does everyone recognize this river right here? Coming out and out to the ocean. Excellent. Yeah, that's the Columbia River right down past Wallula Gap, the river, the river right close to Walla Walla. Here it is as it moves down past Astoria and out into the ocean. Compare that with this river system right here. Does everyone see this river system here? This is the Mississippi River, which is flowing down into the Gulf of Mexico. And notice how dramatically different it is. The um, the Columbia River has an estuary. We kind of have this big broad opening where the Columbia River meets the Pacific Ocean. What do we have in the case of the Mississippi River? We have a huge delta, right? And we talked about deltas when we talked about the Mississippi River and the Atchafalaya. These are all distributary channels that are dumping sediment out into the Gulf of Mexico, and it's stacking up. And so, what the heck's going on here? Why, in some coastal situations, do we form a delta, and in others we form an estuary? That's an interesting question. And honestly, this is something I didn't even get until I was much older. And now I'm really excited to kind of share with you kind of what's driving these fundamental differences in what coastlines look like. And really, our first order control on what a coastline looks like is related to the tectonic setting. And so we have wildly different tectonic settings between the Pacific Northwest and the Oregon-Washington border, where the Columbia is coming into the Pacific Ocean, and then down in Louisiana, in southern Louisiana, where the Gulf of Mexico is, and the Mississippi River is dumping into the Gulf of Mexico. They're totally different, right? Totally different tectonic settings. Whoops, wrong way. Sorry. One is a passive margin, and so this would be a great case of the Mississippi River. And so on on a passive margin, what we don't have any tectonic plates being subducted underneath like we have in an active margin. And so right here, what we end up with is kind of a consistent kind of slope as we move out from the land out into the ocean before we hit the continental shelf. And so because of that, we end up with relatively shallow water, and our sediment that dumps out of the rivers essentially just gets stacked up. There's nowhere else for it to go. And so it gets dumped out, building a delta, and then some of that gets picked up by wave action and maybe forms barrier islands out in the ocean. We'll talk about barrier islands in our next lecture on coastal landforms. So we end up with, because it's not a particularly tectonically active region, we end up with kind of a broad coastal plain, this flat zone at the margin between the ocean and the continent. And then we might end up with what's called a Piedmont region, which is a deeply eroded landscape associated with tectonism in the wave a long, long time ago, millions to hundreds of millions of years ago. So these are old faults, these are active faults. So because of this passive margin, this quiet margin, the sediment gets dumped out and there's nowhere else for it to go. Sad, but true. Compare that now to an active margin. So here's an active margin setting. Think the Oregon coast or the Washington coast, where we have a plate, an active oceanic plate that's being subducted currently underneath the North American plate. So this would be the Juan de Fuca plate being subducted under. And now when you have rivers that are dumping out their sediment, there is some place for that sediment to go. We end up with a trench, and that sediment can get dumped down into the trench at the boundary between the two plates. But what's also really important, not only can that sediment fill the trench, but then it gets recycled. It gets dumped down into the trench as that plate gets subducted. And so because of that, we don't end up with this blob of sediment at the coastline. So we form an estuary. We've got this drowned river valley as opposed to a delta where you've just stacked up sediment. And so this active margin setting is wildly different. You can take another class and talk about all the exciting stuff here with like cascade volcanism. But in terms of the morphology of the coastline, the difference here between an active and a passive coastline tell us kind of first order what our coastline is going to look like. Because of this active margin, not only are we going to have estuaries, but we're going to have relatively rocky coasts, right? We're going to have the accretionary wedge, we're going to have uplift, and so you generally see high relief along coastlines associated with the Pacific Northwest. Now, this is also really, really important when we start thinking about things like sea level rise, because not all coasts are created equal. If you have an area where you have a really, really slow elevation changes, you move from the ocean onto the land, then as sea level goes up, you're going to flood more of that land. If you have a steeper landscape, then as sea level goes up, not as much of your land is going to be inundated. Okay. The second really important control, the second big control that has a strong secondary control, it's not the primary control, the secondary control on coastlines is the availability of sources and sinks. And so that's going to dramatically influence what the coast look like. Where is the sediment coming from? How much sediment is there? Where can the sediment be stored? How much space is there for storage? That's our second big control. So let's look at some of these. First here, let's think about the sources. A big source of sediment into a river, into the ocean are going to be rivers. So what type of rivers do you have along your coastline? What is the sediment load of those rivers? So here we're looking at a river that's dumping out into, not the ocean, but a lake in this case. But you can see all this muddy water here, right? This is sediment that's dumping down into the river right here. Or excuse me, the sediment that's dumping from the river out into the standing body of water. And so river input is going to be a really important control. Another big control is going to be glaciers, right? Where you have glaciers that meet the ocean. These are what we call tidewater glaciers and down in the ocean. Here, any of that sediment that's taken a free ride on the glacier is going to get dumped off into the ocean. And so glaciers have a really, really important ability to move sediment onto coastline. Okay, another important source are going to be coastal sediments themselves. Are there abundant sources of sediment along the coastline? Do you have high relief? And so you can get lots of mass movements that are going to dump sediment down into the ocean. Do you have long beaches where you're going to be having sediment that can move along those beaches? So coastal sediments are another important source. Okay, let's move on to the sinks now. All right, sinks. A big source of sediment that gets trapped along coastlines is associated with dunes. So dunes are sandy features. We'll talk about them when we talk about aeolian processes. But imagine you've got all that sand that dumped out of the river onto the beach. The wind can pick up some of that and blow it up back onto the land, and you end up with these dune features behind the beach. So dunes are a really, really big sediment sink. Another big one are lagoons and estuaries. So an estuary is where a river meets the ocean, and a lagoon is where you have essentially a backwater where you have kind of a confining area, like we've got coastline right here. Then the lagoon is kind of brackish water behind that is disconnected mostly from the open ocean. So lagoons and estuaries provide really important source places for sediment to get stored along coastline. Our other really important sediment sink on coastlines is offshore. Offshore is really, really important as well. So look at this here. If we've got, say, a drowned river valley, so here's the current coastlines. Everyone see the current coastline? Barely need to draw this on eye. Okay, so here's the current coastline in red right here. What if the ocean, the coastline, what if ocean levels had receded and you end up with a coastline that's further out? That means that this river has to travel across the continental shelf. And as it does that, it can incise down into the coastal, into the continental shelf right there. And essentially, when the sea level comes back up, then you drown that river valley and you've got this giant gaping chasm beneath the water that is another place where you can store sediment. So drowned river valleys could be a really, really important sink associated with coastal regions. Of course, when we're talking about these drowned river valleys, these are really, really common along coastlines associated with glacial interglacial cycles. Because remember, at the LGM 21,000 years ago, coastlines the ocean level was about 100 meters lower. And so our rivers had to go that much further across the continental shelf before they reached. Okay, so those are kind of my introduction now um, to the different processes that excuse me, the different, yeah, the broad brush stroke processes that shape coastlines in terms of tectonics, sources, and sinks. Now we're going to talk about a couple of really important processes that shape individual coastlines. Um, there's going to be two we're going to discuss before the end of our lecture today. We're going to do this one right now, really quickly, tides, and then we'll get on to the next one. So tides are going to be another important control on the shape of the coastline. And so tides are associated essentially with the gravitational pull between the Earth and the moon. And so what happens is when the Earth, when the moon is close to the, to whatever region that your coastline, when the moon is right there close to it, you end up with a gravity bulge associated with the water being pulled by the gravity of the moon. And so we end up seeing a tidal cycle as the earth as the earth spins. And so we end up kind of with tides with as that bulge changes, the center of that bulge in the oceans, the tides go in and the tides go out. So it's associated with that gravitational pull of with the moon. Now, there's another important thing in terms of tides. Not only is there going to be a high tide and a low tide, depending on where the moon is associated with the coastline you're talking about. But the other really important thing is we're going to have what's called neap tides and spring tides. So neap tides and spring tides have to do with the orientation of the moon and the earth relative to the sun. So when we have neap tides, the moon is acting in a 90 is acting its gravity is acting 90 degrees from the pull of the sun, whereas when we have spring tides, the moon and the gravity of the sun are acting in parallel. And so because of that, because it's an additive force, you end up with higher tides. So look at our tide range here from low, um, 0 meters, to high tide up to maybe say 3 to 4 meters. That difference, and then at a neap tide, maybe it's only 3 meters. So the difference there between the spring and the neap tides is the orientation between the gravity pull of the earth, the sun, and the moon. So spring tides and neap tides, think spring rejuvenation, bigger tides. I don't know. Something to keep that in your head. Neap tides are those smaller tides. Also, the geometry of the coastline is going to have a huge, huge impact on the tidal range as well. So probably the most famous example of this is the Bay of Fundy up here off from Nova Scotia. Um, and so the Bay of Fundy is famous for having, what's it say there? Over 15-meter tides right in the Bay of Fundy, 49 feet. And so our picture on the bottom is showing the difference between high and low tide. And so the Bay of Fundy tides have to do with essentially kind of we've got this perfect channel. And look, as we move into the Bay of Fundy, um, the tides increase as we move into the Bay of Fundy. And what that's associated with, we're looking at kind of the from deep water to shallow water. And so all of that water kind of gets forced into the Bay of Fundy. And so you end up with this huge amount of water in the Bay of Fundy that gets forced all the way up to the end. And that's what causes these huge dramatic tides every day, is that water getting pushed into this really narrow space and then coming back out. So the geometry of your coastline is going to be really important for controlling the tidal range, which then in turn is going to dramatically control the morphology of the coast. Okay, now that we've done that, let's talk about kind of the dominant driving mechanism for changes along coastlines, and that's going to be waves. So you cannot understand the movement of sediment along coastlines unless you understand waves. So let's get in here and talk about waves and kind of how we can quantify waves and what they tell us about coast. Okay, a couple of terms we're going to have to define here. Our wavelength, oftentimes in equations represented by lambda, is equal to the distance between wave crests. Wave, yes, right, wave, and I'll show a picture, don't worry. Wave crest to crest, that is our wavelength represented by lambda. Coming down, next up is our period, our wave period, which is what we call time t, and it's the time it takes two wave crests to pass the same point. So if you've got a point right here, And then here's the first wave it passes, then you time to the next wave that's passing. So wave period is just the time it takes for those wave crests to cross the same point. So this is the wave crest, passes in front of you, one, time it takes for that next wave crest to come in front. That is our wave period. Um, our next term we have to define is our wave velocity, which is the ratio of the wavelength to the wave period. And that tells you how quickly those waves are moving across the landscape. How quickly those waves are moving in water. Okay, so here we've got the picture from your textbook showing these different variables right here. So wavelength going crest to crest. Here's our crest. Here's our next crest. That is our wave crest. Then as that wave passes by, the time it takes for the crest to pass the same point, we call that the wave period. Then how quickly that happens, that is our wave velocity. Okay. Another really important thing when thinking about waves is that waves refer to the movement of energy, and we're watching energy pass, but we're not necessarily watching the movement of individual water molecules pass. So what we see is that with waves, an individual water molecule has this cyclical motion as it moves in these clockwise circles. So clockwise circles here, this is the motion that any particular water molecule is going to take as it's going in the wave. So if I'm a water molecule sitting here and the wave comes over me, I'm going to rotate down and back up each time with each one of those waves. So that is really important. And notice that the size of the trajectory that water molecule is going to take depends whether you're on the top or the bottom of the wave. Towards the top of the wave, that movement is really big, and it gets progressively less as we move deeper into deeper water. Now, at a certain point, no longer do you actually have movement of water molecules associated with the wave. We call that the wave base. So the wave base. And so if you're underneath the wave base, you don't even feel the wave going over you. You can just be standing there. So that's the wave base, and that's going to be really important for understanding how waves interact with coastline. So here's kind of a nice animation just showing kind of the individual trajectory of a molecule as the waves go by. So we get kind of this pattern of movement, cyclical fashion associated with our waves. So I think that's really useful for thinking about movement of the wave, that energy, the movement of energy versus the movement of an particle. Okay, so I already mentioned this, but I'll just say it again here. Our wave base, by definition, it's the depth limit to which the passing wave has influence on the seabed, and that's why it's really important. Again, if the seabed is deeper than the wave base, then you're not gonna be moving any sediment off the bed. Okay, let's move on. Another term I want to talk about is associated with kind of waves out in the open ocean. And this is what we call wave dispersion. Um, and so basically, most waves, as we see in the ocean, if we're not talking about a boat moving across the surface, most waves are generated by wind and wind blowing across the surface, which is what makes our waves. Um, and so because wind is going to be moving at different speeds, we're going to have different types of wavelengths. However, those wavelengths are going to kind of travel at different speeds. And so because of that, waves start to sort out by size. And so your larger waves are going to move slower. And so because of that, what you end up seeing is a regular kind of progressions of waves. And those are waves of all the same size because they're moving at the same speed. Any smaller waves would have already moved by. And so this is what we call wave dispersion, and allows us to kind of see this very consistent size in the wavelength out in the open ocean. It's because of this wave dispersion, waves moving at different speeds. If you're like psyched about this, if you're like, oh my God, this is so cool, this is all essentially physics. So go take a bunch of physics classes and you can learn a lot more about the properties of waves. Okay, moving on. Uh, Based on wave dispersion, we oftentimes see a regular spacing of waves out in the open ocean. We call this swell. So this is swell. Isn't that swell? It's regularly spaced waves. These have low, gently rounded crests, and these can travel over great distances across the ocean. That's if you've ever been out in a boat out in the ocean, kind of every once in a while you bob up and down. That's your boat as the swells moving by. Okay, let's talk about what happens with that swell as it starts moving towards coastline. Um, as that swell approaches the coastline, you move from a really rounded crest wave to a wave where you're starting to build up the top of it and it's starting to increase the height of the wave and the steepness of that swell is increasing. We call this a shoaling wave. And shoaling happens when we're in water that's shallower than about half of the wavelength. That's when waves start to shoal. And finally, what happens as that wave starts to steepen, it can no longer support the weight of the wave, and the wave crashes over on itself. And we call those breaking waves. The breaking waves, kind of that surf you see, that's the breaking of the wave. Um, okay, let's look at some more details of this. Um, so that elliptical path that we identified here, that changes as you move from the open ocean and move out onto the shoreline. So this has to do with the depth of the water. And when we're below the wave base, the velocity of the water molecules at the top, how am I going to do this? Well, I'll just point to it. How about that? Okay. The water molecules at the top are moving at the same speed as the bottom. Okay. Um, However, watch what happens as we start moving our wave towards the shoreline. We're going to start to shoal as our depth becomes 1/2 the wavelength. We talked about that shoaling wave. And what's happening here is our particles at the bottom start to slow down as they interact with the bed right here. They get some friction and those start to slow down. But at the top here, that wave's still moving at the same speed. And so what happens is that wave gets steeper and steeper until it crashes and forms that breaker. So out in the deep ocean, we get these circular paths, and all those paths are kind of moving at about the same speed. When we're out in the deep ocean, we can estimate our wave velocity as our wavelength divided by our period, or another way about thinking that is gravity times that period divided by 2 pi. That's another way we can estimate waves in the. Whoop, we got that one off. Let me turn that back on real quick. Okay, and we're back. So this is our wave velocity here. We've just calculated our wave velocity, that wavelength divided by the period. If you can't measure that wavelength, you can actually just measure this by using the wave period. Okay. Now, as those waves start to move towards the shoreline, our wave base interacts with the ocean floor, and as it does, you get friction that slows down the particles at the base, the molecules at the base versus the top, and our waves will start to shoal. So when a wave enters water, it begins to shoal. Well, excuse me. When a wave enters shallow water, it begins to shoal. Um, that wave shoal ratio will increase proportional essentially to the depth of the water. Okay, so we can kind of actually quantify this. Um, and so when the height of the wave equals about 1/7, hold on, let me make sure I got that right here, right here. When the height of the wave equals 1/7, which means the wave height exceeds 0.14 the wave length, that's when the waves become unstable and they start to break. Um, so that's kind of important here. Our wave height, height over pi, when that equals roughly 1/7, that's when we start to get our waves crashing. Okay, as we move to shallow water, we can quantify that velocity of the wave as the gravity times depth raised to the 1/2, 0.5. That's how we quantify as we end up with our shoaling and breaking waves. That's how we can approximate the velocity. Okay, another really important aspect of this has to do with essentially how quickly you develop those, how quickly you change the wave, uh, the depth of the ocean. And so the depth of the ocean, if you have a really steep coastline versus a very gentle coastline, that's going to determine the type of wave of shoaling wave you generate. And so if you've got a very gentle coastline where it goes very gently out into the ocean, um, that beach morphology or that coastline morphology will generate what are called spilling breakers. These are relatively low energy waves that kind of just spill out and splash along the coast. So this is really common along flat coastlines. Think places like Florida. Um, as we steepen our coastline, we end up developing a different type of wave, what we call a plunging breaker. And a plunging breaker is the one that ends up with a really, really steep crest. These are the ones that the surfers like so they can surf through this thing. So that's a plunging breaker. And plunging breakers develop along steeper coastlines. And then beyond that, what's called the surging breaker, which doesn't develop that really nice kind of tunnel. It just basically just crashes in on itself in steep, very steep coastlines. We call those surging breakers. Okay, another really, really important aspect of waves and coastlines is the development of what we call longshore drift. Longshore drift, because that's going to dramatically impact the movement of sediment along coastlines. Longshore drift develops because we end up preferentially pushing water onto the shore associated with a dominant wind direction. So here we've got the wind that's kind of pushing the wave onto shore at an angle, right? Because this is roughly the coastline out here. Does everyone see that? So what's happening is the wind is pushing these waves onto the coastline at an angle relative. It's not perpendicular, it's at an angle. And that's going to be really important, right? Because what happens is our coastlines, our waves, the path of sand along the coastline is going to follow an asymmetrical path. So as our waves are pushing the sand on shore, they're going to follow that wave direction. But as that wave rolls back out into the ocean, it's going to go perpendicular to the coastline. And so because of that, it gets pushed on at an angle and then pulled back out perpendicular. Pushed on at an angle and pulled back out perpendicular. Because of that, you see asymmetry, a preferential direction of movement. The sediment is going to be moving along the coastline in the direction of the prevailing wind direction, the dominant wind direction that drives waves. That's going to push the sediment out and then come back horizontal. Okay, here's a nice animation of that. So this, I think, does a really good job of showing that preferential wind direction going across the page here. And then you can watch an individual particle of sand on the beach as it gets pushed up at an angle and then pulled back out perpendicular to the coastline. So this is what we call longshore drift or littoral drift. Okay. Last thing I want to talk about, oops, oh, sorry, I went the wrong way, but that's good because I should mention as well that when we see these beautiful landforms, these recurved sand spits that extend off the land, things like you see at Cape Cod and places, those are associated with longshore drift. And longshore drift becomes a huge problem with sediment erosion, and so we have to build things like jetties here to control movement of sediment. We'll talk about that later in the week. Okay, my last point for this lecture is another really fascinating thing happens along coastlines, and that's what we call wave refraction. As our waves go from deep water to shallow water, the velocity of that wave changes. The velocity of the wave changes, and as the velocity of the wave changes, the angle that the wave is taking, the direction of the wave changes too. And so what happens is, because of that, as the water comes ashore, we end up kind of focusing the wave along points that stick out along the coastline. And so the wave water will refract and it'll be focused in along what we call a headland. And so waves are, this is the headland right here, two headlands right here. Because as the wave's coming ashore, it shallows towards the headland. The headland is going to be the shallowest water. And so the wave refracts towards it, it slows down and bends. Those waves bend. And so a wave coming in here, it's going to start to bend towards the headland. So because of that, you end up focusing erosional energy along headlands. Does that make sense? As you're focusing that energy, the waves move towards the headland, they bend towards the headland, you have greater velocity and more force associated with more water that's being forced towards the headland. And these become areas of significant erosion. And therefore, we often find headlands to be very, very steep parts of the landscape. Opposite that, where you've got basically a bay, your wave isn't being concentrated in, it's being kind of dispersed out. And so because of that, your wave energy here is very, very low in the bays. And so because of that, you have low velocity in these bays. And that means that you preferentially deposit sediment there because you have lower energy. So the headlands erosion, the bays is where you get deposition, and that's where your beaches are going to be. So that's what this picture is right here, showing a headland right here, and then in the bay, that's where the beach is. And that's because the wave energy all gets focused here along the headland, and you get erosion. Okay, I think I've got another picture of this. Yes, here's a picture from California. You can actually see these waves, and they're getting refracted and focused. That wave energy is being focused onto the headland. Okay, the opposite of that would be in the bay, or in this case, a cove right here, where we have kind of the opposite of a headland. We have an inlet, and so because of that, wave energy is focused towards the headlands, and we end up with dispersive energy or no energy, disperse the waves. You end up depositing sediment along the cove, making beaches. All right, great job. That's all I've got for you today. We'll be continuing on next to think about how waves make dramatic different landforms along coasts. So good job, everyone, and we'll see you soon. Have a good day. Bye.
We'll stand on board as brotherhood. We'll rule the sea, just you and me. Let the devil take another.